Good afternoon. I'm Patrick Beard, and during the first half of this session, I'm going to be talking about advancements we've made to the Objective-C and garbage-collected runtime systems. And later on, Blaine Garst will be coming up and telling you about blocks, a major advancement we've made to the C programming language. So first up, I'm going to talk about performance. And this is the kind of performance that everybody likes. It's for free when you run your programs on Snow Leopard. So before Leopard, there was pre-binding. Shared libraries had their own assigned address ranges, which were maintained by update pre-binding, and they were all loaded one at a time, memory mapped one at a time. In Leopard, we added the shared library cache. This caches copies of all the pre-bound shared libraries and memory maps them all at once. By doing that, we save space, we save time, we're able to share all these libraries across all the processes of a particular architecture. And at launch time, performance was significantly improved. In Snow Leopard, Objective-C is now part of the shared cache. All of the selectors used by all of the Cocoa frameworks are stored in a unique table, and all the references to them are fixed up in all the shared libraries. That amounts to about 700K of shared data in a 64-bit process. That sharing allows processes to launch even faster. But we also sped up message send. The Objective-C 64-bit compiler now knows about a set of 16 selectors, which it uses. It speeds up the calls to those by using a hybrid virtual function table. So there's a few of the selectors in that list, the common ones you might expect. Now, we only use the top 16 for a very important reason. That speed up that you get by doing this comes at a cost, a space cost. It's an extra word per call site, and of course it's the 16 words for the vtable. But this set of selectors covers about 70% of all message sends that happen globally in all programs, all Cocoa programs. So we're able to speed up by about 40% all of these calls without increasing space usage too much. So we save space in the previous optimization, and here we're using a little of that space to get some speed. Also, our vtables, unlike C++, are non-fragile, just like we have non-fragile instance variables. So there's no C++ style release-to-release binary incompatibility. The vtable slots are actually assigned at runtime and can actually be unassigned and unused. You'll occasionally find that you have some methods you want to call that would be using a vtable dispatch and retain release code, but not in GC. I'll tell you more about that in a minute. So to get a feel for the gist of how this stuff works, let's look at a simple program that sums an array of NS numbers. Object@index is one of those accelerated selectors. So let's zoom into the message send. For every unique message send in a program and across all the frameworks, there is a message structure generated by the compiler. It's static, and it contains two entries, the selector and a function to call to actually do the message send. First time it's called, the message send function is message send fixup. This is where the vtable slot assignment is done, and it changes the actual message structure and converts it to the faster one. So all subsequent calls go through that. And as I said earlier, this one takes about 7 instructions to execute versus the 20 or so of the standard Objective-C message send. So it's fast because it's a direct map, doesn't have to do any hashing. When you're debugging vtable dispatch code, you'll see some changes when you're looking at the symbols. You might encounter Objective-C message send fixup, which I showed you. Objective-C message send fixed up will appear when you make a call that was supposed to be a vtable dispatch, but it didn't actually end up using a vtable dispatch. This would be like retain and release in garbage collection mode. The runtime says, we don't need to accelerate those. They don't do anything. So when you see these symbols in the debugger, don't worry about it. Don't panic. It's just like Objc message send. Just you can step through your methods as ever. So that's vtable dispatch. We've also enhanced the crash reporter so that it can give you more information in the unlikely event that your program crashes. When you call Objc message send, the old style crash logs look like this. You just saw some obscure information, you go look at the register, you scratch your head, you go, well, what happened? Well, I know it was something from this method that caused the crash. The new one gives you the name of the selector you were trying to send. Thanks a lot, Greg. So I don't think you're going to applaud for this, but the next feature I want to talk about is synthesized instance variables. So in Objective-C 2.0, you can actually synthesize the accessor methods for your properties. And if you're using the 64-bit ABI or the iPhone OS, you can leave the instance variables out. Fortunately, there was one glitch. The compiler would generate the instance variable, add it to the class, but you couldn't touch it. You couldn't actually reference it by name. So this is fixed in the Snow Leopard compiler. GCC 4.2 and Clang now both can handle this. But if you're writing code that needs to compile for iPhone or the simulator, just go ahead and declare the instance variable. It works just fine. So now I want to talk about a brand new feature of the Objective-C runtime in Snow Leopard. It's called associative references. So imagine you're writing an application, and you get the bright idea to have, whenever a window, every unique window kind comes to front, it plays a sound. So you could model this using a category. You just say, well, all my windows will have a property called sound. And you could use key notifications and use that category and see if the sound exists yet, dynamic or lazily bind it to the window like this. So whenever the sound window comes to front, a sound is loaded and it's played. Whenever the window goes to the back or is no longer front, it stops. So how would you write a category like this? When a language like JavaScript or dynamic scripting language, you can add instance variables on the fly. It's no problem. But Objective-C doesn't support instance variables being added to objects on the fly. So we have a couple of problems we need to solve to make this work. One is, where are you going to store the sound? Where do you put it? And then how do you retrieve it later? So this seems like an ideal candidate for a map table, a global map table stored in a global variable. It's off to the side, and it would use weak keys and strong values. But if you're writing a garbage collected program, which I hope you are, this can cause subtle leaks if the value object points back to the key. It creates an uncollectible cycle. That's because the map table is global. It's not a problem in this case because the sound doesn't point to the window. The harder problem is lifetime. How do we find out that the window has gone away or is about to go away so we can clean up after it? In this particular case, we get a notification that Windows closed. But in general, you might want to try solving this problem by subclassing. But this particular scenario, we want to actually catch every window type. You know, NS windows and NS panels and save panels and things. And some of them, we're not going to be able to subclass. So the solution, it's very simple. We have a new API called associative references. This is a complete implementation of that category. So notice there's a static variable called sound key. The address of this variable is what's important here. It is used as a globally unique identifier that represents the association between a window and a sound. So to create an association between two objects, you call obj_c set associated object. You pass it a pointer to an object, in this case the window, the key, which is the unique identifier, the sound, which is the value object, and a final parameter, it's called the policy. In this case, the property attribute said, we're going to retain the sound. So this tells the associative references system, go ahead, when you create the association, call retain. So here's the API, a piece of it. There's another function for getting. But you'll notice these policies are defined to correspond to the property attributes assign, retain, and copy. So it's very easy to implement properties in terms of associative references. In fact, I'd say it'd be a really good idea to be able to synthesize properties. There's no syntax for this yet. So there you have it. In Snow Leopard, Objective-C programs launch faster, the common selectors are accelerated, and you now have the freedom to associate arbitrary objects with each other. Pretty cool stuff. So now I'm going to tell you about what we've done to improve garbage collection for Snow Leopard. So in Snow Leopard, since Leopard, all COCO frameworks and all core foundation frameworks have supported garbage collection. We've added a ton more frameworks for you to use. We still support that. We're going to be supporting that from now on. What's more, 64-bit applications, the system applications, system preferences, and screensaver and automator are now using GC in 64-bit mode. So Apple is embracing 64-bit and GC at the same time, and we would like to encourage everybody to do the same. In Snow Leopard, garbage collection runs even faster. In Leopard, the garbage collector runs in two modes: full collections, which collect lots of objects, and generational collection, which doesn't collect as many, but it runs about twice as fast. The generational collector was designed with short-lived objects in mind. The thread local collector is based on the hypothesis that there are lots of threads, there are going to be lots of threads in Snow Leopard that allocate lots of temporary objects. This is actually the same rationale behind the auto-release pool itself. You make an object on a thread, you put it in the auto-release pool, you're done with it, it goes away on that same thread. The thread local collector provides even faster allocation because it uses a thread local cache. It also collects faster because all it has to do is look at one thread stack and all the objects reachable from that. So the full and generational collectors run in about a time that's proportional to the size of your program's heap. The thread local collector is more efficient. It only has to collect as many objects as a particular thread is allocating. It also is able to return that memory that it collects directly back to its allocation cache, which is a huge efficiency win. And it's more scalable. As I said, the amount of memory it has to look at is proportional to the thread, the single thread. So each thread local collector only has to worry about one thread. The thread local collector only manages a particular set of objects, a particular size range, between 1 and 96 bytes in 64-bit. But all the classes on Snow Leopard, 68% of them are in that size range. In fact, 99% of the objects we provide, their classes, are less than 1K. So it simplifies the collector to only support the smaller size. It makes it faster. It also only supports objects that have retain counts of 0, which which is what you get when you create COCO objects. Core foundation objects start off with retain count 1, and you have to CF release them to get rid of them. They're off the table for now. So the thread local collector, or TLC for short, so I don't trip over it too much, works best if you trigger it explicitly. If you happen to know there are some objects that are ready to be collected, then you can use one of these APIs. You can use the auto release pool API. That works great if you're writing code like, well, a system preferences pane, for example, which needs to be retain release in 32-bit and 64-bit GC. Otherwise, you can use the garbage collector, NS garbage collector API, or obfusc collect. When you do that, you're only actually giving a hint. If you want to force the collector to run and you want to see if an object will go away, you can use exhaustive collection. And that is provided us also in 2 flavors. That will always run TLC on the current thread, and it will push the background collector to run even more aggressively. Thread local objects, we call them local for short. If they escape the control of the thread local collector, we say they go global. This happens in response to calling CF retain, for example. When you call CF retain, this makes an object ineligible for a collection. It allows you to store that object anywhere. You can store it in malloc memory, and the collector won't get rid of it. Well, then the thread local collector won't get rid of it either. Simply assigning it to a global variable does the same thing. We use a write barrier, and that tells the thread local collector where the objects are being stored if it's about to lose control of them. Also, the weak or associative references, if you use that, objects stop being local. The reason is those systems use locks, and we want to keep TLC really fast. Finally, if you have a local object and you assign it into an instance variable of an already global object, that will make it go global. A good example is you create a new view and you put it into the view hierarchy of a window. That causes all the objects connected to that view to go global. So now a couple of cautionary statements. You probably know this, or maybe you learned it the hard way, but it deserves repeating. When you use the auto release pool, objects might go away. Their dealloc methods might be called. So dealloc methods can take locks. If you happen to be holding locks from your code, it's probably a bad idea to call drain, because you might deadlock your own code. The same is true now under garbage collection with thread local collection. Same thing can happen. A finalize method might be taking a lock. So if you hold locks, don't call into the collector. And better yet, don't write finalize methods at all, or finalize methods that take locks. So that's the collector, that's thread local collection. Now I want to talk about our performance tools. Instruments has been enhanced to know a lot more about garbage collection in Snow Leopard. The garbage collector instrument can actually show you a log of all the collections that have occurred, and it will tell you their kind and how much time they're taking. So right here I'm showing a local collection has run, and it collected 100 objects, and it did that in about a third of the time of a generational collection, which also is collecting 100 objects. As I said before, the time to run these collections are proportional to the number of objects being managed. Also over here on the right side is the stack crawl where that collection occurred. So you can monitor where you're calling into the collector. It's a great idea to call in on a shallow stack because there's more likely there's more garbage to collect. The object graph instrument tells you about how your objects are connected to each other and to the heap and to global variables. So here, I'm showing a path from a global object, the NS application, to its delegate. And here, it actually shows the name of the instance variable that's connecting it. So you can use this to look at long chains of objects to get a grip on why an object isn't going away, what it's connected to. You can get a snapshot of this connectivity. Finally, the leaks instrument works with garbage collection. The only objects you're going to see in this list are objects that have a retain count that's non-zero, because those are the only objects that can leak in a garbage collected program. The other kind of leak is overrooting, but we don't show that here, and we don't really call it a leak. You can go find it in the object graph. We also show the list of leaks, and over here on the other side we show the allocation stack crawl, which is a really important way to start finding leaks. Look where it's allocated. Now I want to talk about GDB. GDB is always available when you're debugging in Xcode or on the command line for you diehards. So we added 3 new commands to it. They're all prefixed with info. One is totally general purpose. It accesses the malloc history information. You set a particular environment variable, and the allocator stores stack crawls for all the allocations. Well, it also works in garbage collection mode, and it tells you about all the places objects were allocated and all the places the collector got rid of them. So you can find out why an object that maybe is corrupted doesn't exist anymore with it. Very handy for that kind of debugging. Info GC references gives you all the pointers to a particular object that there are. And GC roots gives you all the pointers plus all the paths from the roots that lead to your object. So this gives you similar information to instruments. Also, there's some handy one-liners. You can call obfusc collecting enable from the debugger and find out, are we really running the collector? Sometimes things don't happen like you expect because you're not actually running the collector. CF get retain count tells you if an object has a retain, therefore it's not going away. Malloc size you can call on any kind of allocated pointer, malloc or the collector's memory. It works with either one, tells you how big the object is. And obfusc is finalized. You can use during finalization and find out if a particular object, your object references, is about to be finalized, is going away. You can use that to find out whether it's safe to store that object or do other operations. So we have some environment variables. To highlight the important ones, auto use guards is now available, which gives you guard pages. It always allocates at least 2 pages, puts your object in the first one, and allocates a read-only page after it. It's great for detecting buffer overruns. You've got to have a lot of memory, but it can be really handy. There's also auto-reference count logging, which, as I said earlier, enhances the malloc history. It will give you all of the activity the collector observed for reference counting. And it only logs the information that the GC itself sees. When you're using CF retain, only the first CF retain on an object will actually talk to the collector. So it's actually kind of handy because it's going to be less voluminous to go through those logs. So the collector is now open source. We released the 10.5.3 version of it late last year. It's the version of the collector that was shipped as part of 10.5.3 Leopard. And here's the link to it. It's released under the Apache open source license version 2. And it's not just for Objective-C. The collector is actually language agnostic. The open source project MacRuby is using it, and we'd like to encourage other projects to use it too. So if you're interested in doing that, please contact Michael Jurowitz. His contact information will come up at the end, and let us know. In March, we presented our extensions to C, including garbage collection and blocks, in a paper to the C Standards Committee, to the working group. And there was interest in it. And if you're interested in it yourself, I have published the link to that paper on their website. So thank you very much. I'd like to invite my colleague now, Blaine Garst, to come up and tell you all about blocks.
Thank you, Patrick. So I want to tell you all about blocks. I'm borrowing a few slides from a talk I gave a little bit earlier this afternoon, but here you're going to learn all about the syntax. You're going to learn all about lifetime issues. You're going to learn more about Objective-C specialization. You're going to learn the full story. It's not that big, but it's a little bit bigger. But if you didn't come into my talk earlier, I want to start over again. If you've ever programmed with lambdas, then of course you've been using either Scheme or Lisp. If you've programmed in Smalltalk, you see those things in square brackets, that funny syntax, and that was called a block. It was actually an object for them. Every if-then-else control structure kind of thing was an object. That code in those square brackets was actually a block. Interesting idea. In Ruby, we also see this concept coming back again. In Lisp and in Scheme, this concept of having sort of this function that you pass to somebody was called a closure. And the reason for that was that you got to carry along the variables locally for you. But if you're a programmer in C, or one of its related families, Objective-C or C++, or the union of those two, Objective-C++, you've been out of block for a long time, but no longer. In Snow Leopard, we have the same kind of a construct. We call it a block, and it looks like this. It's that funny caret symbol ahead of, a curly brace compound statement expression list. You are creating sort of a local function and passing it off to something that's going to do something more interesting with it than that you want done to it. So in this case, what's going on is we're carrying along the value D in that local compound statement kind of block that you're passing along. And we do this very efficiently. Those other languages were not only garbage collected, but they were mostly interpreted. And that's a very big expense. And of course, C is neither garbage collected nor interpreted. So we know how to do this in a highly compiled, highly optimized way. So let's see how that repeat function might be implemented. So the syntax we use to declare a block reference is just like function pointers, except we use the caret symbol. So semi-familiar syntax and form, it's not so bad. Except as a parameter, you got to worry about the return type and the parameters, and when you're passing one of or when you're trying to declare one. And so we highly recommend that you use a type def to kind of hide the clutter. And so if you use the type def, the implementation of the repeat function becomes fairly simple. It's passed in a block, and then it simply calls it like it's a function pointer, like a function. So you can pass parameters, get the results back. It's very natural to use as well as to create. So why blocks? It leads to smaller, easier, more precise code. Who can argue with that? We found over 100 uses inside Snow Leopard already, and boy, we've not closed the book on that yet. There's going to be even more coming along. For the most part, we use them for callbacks. We use them for concurrency using Grand Central Dispatch, and we use them for all the 40 years of accumulated wisdom on how to use closures, and that is for sort of these iterate and map and reduce kinds of stuff. So I'm not going to touch on these 100 APIs. I'll give a couple examples here to give you a flavor of what's there, and all the details of syntax and stuff. So my canonical example for this is qsort R, which is the existing way to get to 50 years worth of collected wisdom on sorting. So if you have a particular problem where you need to, say, sort according to different parameters, not always the same way, then what you have to do is supply a callback argument to the qsort routine such that whenever it calls the compare function, and the compare function takes the left and the right, and then it will also then pass you this callback parameter that you've supplied it. So in practice, let's say we're trying to sort some kind of array of people objects, and age first might be one of the options that happens sometimes, and other times other things. So the first thing you have to do is declare this custom structure somewhere in your code you have to write the custom compare function, which takes that context pointer, does a lot of casting, gets to the thing of interest and does its thing. You have to, in the function that you're using for QSort, declare that custom structure, fill it in with the right values, and finally, somewhere where you really want to use it, you get to call it. Well, that's a lot of work, especially if you change your mind. You know, how often do you write your code once and you're done? Right? You're always modifying your code. If you have to modify the criteria by which you sort these things, then you got to go modify your code in 3 different places. Could be in header files, could be in separate files, could be bunched here. I mean, it's just a pain. So the better way to do it is with QSort B, which we're introducing in Snow Leopard. And that is, you just simply pass in the things that are important to QSort. And that is the array, the number of elements, the size of each element, and the comparison block. And the comparison block just takes the left and the right. So to use this, you write your QSort B with a natural reference to, you know, the age first thing, and if you need to change it, you just change it, and there is no step 2, of course. Your code is exactly what you want to use for sorting that. So in general, this is kind of, you know, the callback case. I spoke about concurrency. We have a brand new system in Snow Leopard called Grand Central Dispatch. And so the idea there is it's really easy to just kind of push your code off onto a queue, and then that queue gets serviced by some thread somewhere, sometime. And you don't have to worry about it. And so with just one line of code, you can push work off, and there's a ton of talks on how to program with GCD, and it's really a fun system. Another one I think we'll all appreciate is the initialization of a singleton kind of situation. This is a case where you need to do some code once. Now, how many people enjoy writing mutex, you know, pthread mutex declarations? How many people enjoy using them? How many people love to put the little if not singleton, you know, do this kind of stuff for a little speed enhancement? But anyway, there's huge, you know, debates on this kind of stuff. Here is the code to get a singleton initialized. This is it. There's no fancy initializations. You just pass dispatch once, the address of the unique thing that guards your singleton, and then the block of code that is needed to initialize it. And the dispatch system inside Grand Central Dispatch makes it work. It's fast. It's faster than pthread mutexes. So let's recap a little bit. What is a block? So a block is a data structure. It's not a function alone. It is a data structure. And that data structure references that function expression, which in truth is, you know, sort of a hidden function we write for you. But it references that function. It acts like a function when you invoke it. It carries along constant versions of the stack local variables that you use within that block expression. So in the case earlier, the D variable was actually made, there was a local copy of it made when that block was constructed, when that expression was evaluated. So it holds const versions, and that's very cool. When you send that off to some other thread, you carry the memory with you, and you get all kinds of thread, core local kinds of benefits, performance benefits out of that. Sometimes, though, you do need to mutate a variable, and const variables, if you try to mutate them, are going to give you a compiler warning. So in the cases where you need to mutate something and carry the value back, we introduce a new construct with the under block keyword, and it's called block storage. It's a storage class like register and auto for stack variables and static for sort of local globals. So it's a new storage class within C, and you use it in that space. So I mentioned the QSort case, and that's a synchronous case. That's where you hand your work off and it comes right back. But in other callback situations, say with a timer, you need to hand some code off and it'll come back, and then that timer is going to fire and it needs to execute your block. Well, to make that happen, the timer subsystem has to make a copy of your block, and that block copy moves that block onto the heap, and it obeys heap lifetime rules. And so blocks start out on the stack because that's very efficient. That's how, a huge number of uses are made. There's synchronous uses. There's no need to copy it to the heap. But if there is, they are easily copied to the heap where they live for as long as you need them. And so the block subsystem manages the lifetime of all the variables that it references. And that is a real win because there are many callback APIs that take these sort of context parameters where the lifetime of that context thing, it could be malloc off the heap or, well, who knows what its lifetime is and how to get rid of it once you're done using that callback. With blocks, we manage that lifetime in a very consistent and simple manner. So here's an example. I'm going to actually go through this line by line. So the idea here is that we're going to write a function called find key for value. We're going to pass in the Cocoa dictionary, and we want to find the key that matches the value that is sought after. So we're going to return the result. So we need an inner block variable for that. And we're going to pass a block of code to the enumerate keys and objects using block method. That's a new method in Snow Leopard. And it will pass to the block the pairs, the key and object pairs, as long as the stop variable is left alone. So in this case, we want to see whether or not the object passed in matches the sought-after object, and if it is, we set the result to key, set the stop variable to say, no more, we're done, quit now, we're happy, and the enumerate keys and objects method completes, and we return the result. So there are many different APIs we've added in Snow Leopard for different kinds of iteration. It's a great way to express styles of iteration. For example, with arrays, you can pass in a version that goes through the array backwards, and it passes the index in, so you know which index it was. So, we have quite a few different blocks APIs, including ones that'll go and do some work for you concurrently in the background. So there have been talks already on that, and I encourage you to go explore those to find out, some really cool ways to use blocks. Let's talk a little bit more about block variables. So they generally, you allocate them inside, a local, function context or actually inside a block itself. So they're mutable, as I said before. They're shared both with the stack or, the scope of allocation as well as any blocks that reference them. They also start on the stack so that they're very fast. And we have a couple restrictions on them. So you can't use variable length arrays on them because it's hard for us to track that varying number. You get two kinds of varying arrays, and the address of currently is implemented but not recommended because the address changes as we move it to the heap. So let me go back and now let's talk about block literals a bit. I'm going to talk about lifetime a little bit more also. But the key thing for creating blocks, this is the simplest syntax you can use. It's a caret and a set of statements. Now, we're trying to do something really nice for you here, and that is we're going to infer the return type of the block, because it's really kind of a function. And so we infer the return type simply by the presence or absence of a return statement. So that's fine. In this case, printf, there's no return statement in the first one, so it returns a void. And in the second case, the return type is an integer. Many blocks take parameters, no big deal, and the same rules apply about inferring the return type of the thing. We do provide a syntax, though, where you can explicitly state the return type that you want out of this block expression. So in this last example, here's a block that takes a character and returns a character. If the character is greater than quote 0, it's going to return C, which is of type character. Otherwise, it's going to return 0. Well, guess what? 0 is of type integer. So the compiler doesn't like this. It says you're returning character in one place, an integer in the other. What's the deal? And so it'll complain. So there are a couple ways to resolve that dilemma, and one of them is to specify the return type explicitly, and that's what that caret char, that first char part is for. That says this thing is returning a character, and so then it uses normal C language type conversion, and implicitly casts that 0 into a character type as it returns. There are some subtleties we have discovered with inferred return types. It turns out that a single quoted character is an integer. So, if you're wanting this block to return a character, then you can cast the result, and that works, or you can supply that return type parameter. So these are the two styles for resolving these subtleties. I say subtlety number 1 because there's a subtlety number 2. A equal B is not a bool. It's not, it's not a bool by the B, capital B, double O, L, Cocoa convention, or a bool as in lowercase. It's just an int. So if you want a bool back, you have to cast it or, again, redeclare. There is a subtlety number 3. This one stumped quite a few of us for a while. It turns out that an enumeration, no matter how it's initialized, is always an integer. So if you want to return a long out of this block, you again, solutions on the next slide. A very pragmatic problem comes in with real Cocoa API. We have added a new method called sort using comparator, where comparator is one of those type defs that takes a block, of two, comparing two items, and it returns an NS enumeration result. Well, an NS enumeration result happens to be not always an integer. And so you can get a compiler error on this on the 64-bit system. And so the solution in these cases, in the first case, casting works pretty well. But in the second case, you really want to put NS comparison result instead of repeating that cast 3 times, wherever you use our recommended return results. So block declarator syntax. I showed you that sort of function pointer style syntax. Well, okay, remember that. In Objective-C, we use sort of this abstract declarator form, which looks kind of funny because we don't normally pass function pointers in, and you just have to get used to it if you don't have a type def handy. This is the C syntax for declaring an array of function pointers or blocks. It's not very pretty. It gets worse. If you try to return a function pointer or another block, you've got really funny patterns of parameter lists of the thing returned. Anyway, use type defs. We talk about lifetime once again. If we have a function that's going to take a block, then what happens? We declare some memory on the stack. There's room for an int local. There's the initial version of the under block shared variable and the block itself. So if it gets copied to the heap because it needs to be preserved, then what's going to happen? Well, first of all, we're going to move that under shared variable over. We have created, when we evaluated that expression, that block expression, a local copy of the value of local. Here I represent it as underbar local, and that gets copied also. So every version of the block carries that, all the local variables that it's sort of snapped up. And so things are fine. We have 2 situations to think about in terms of how we get rid of that memory. So the first one is the function might return. So, of course, we let go of our explicit reference to that now heap version of under block, and we return off the stack, and we let the heap version of the block expression keep track of the memory. And so that's fine. Second case, say the heap object goes away first. So if the heap's going to go away first, it lets go of its reference to the shared variable. The heap object is reclaimed, but because we're sharing that reference, the stack still has a valid reference to even the heap version of the under block variable. And that's fine. When the stack's ready to return, it lets go of that. The heap memory is reclaimed, and the stack returns, leaving us in our initial state in both cases. We take care of this for you. We never do this copy to the heap for you automatically. This is always an explicit action on your part so that you know what's going on. Now, a subsystem might do it on your behalf, but they make that choice to copy it. But blocks behave the same no matter whether they're still on the stack or whether they're on the heap. That's it's a transparency thing for you. Objective-C specializations. All blocks are objects all the time, even if they're created in .C programs. So here I have a type def for that generic work block kind of thing. So if you want to keep a block and you're in Objective-C, you can send the copy message to it. They're like IDs. Even no matter what syntax you use, whether it's the funny caret style stuff or a type def, you can send the copy message to it directly. We prefer you to use the copy method because if you use the system-provided primitive block copy or block release, the block copies, capital block copies, and the capital block releases have to be matched. And under GC, they can cause unrecoverable cycles. That's not good. So we much prefer the copy method. Auto-release and release work on them as well in the retain release world. So, as I alluded, you can actually send a copy message directly to the caret primitive. That's fine. The nice thing about being objects, being copyable objects, is that they participate as a first-class citizen even with our @property syntax. So this is a very natural way to just build one of these blocks as part of your object design. And it's fully supported, synthesized, all that sort of stuff works. So when you're in Objective-C, you can do a lot of fun stuff inside the block. In this example, we've got a local variable, we've got one of those under block variables, and inside that block expression, which we're going to be copying, we use both the alocal and the block var, and what are we doing? We're actually going to update an instance variable. Okay, what happens when that thing is copied? So alocal will be retained if you're using retain release. That's fine. That's the way that's what we got to do to keep it alive if it's going to persist beyond the function thing. Implicitly, because you use my_ivar, we are going to retain self. So that lets you modify that instance variable within that block. You don't have to play under block funny games or anything like that. So instance variables are remain directly mutable. That under block object is going to be left alone. Whatever value it had is going to be sort of bit copied into this, onto the heap. We've gone around a couple times with what we should do there, but this has proved to be pragmatically the hands-down winner as to how we want to operate on under block variables when they're objects themselves. Some surprises you might run into. We did. A block reference isn't quite a void star. So I tell you, in my code, I go %p, and then the compiler gets mad at me all the time. So I have to put void stars in there. Maybe that'll get fixed someday. I don't know. We've implemented blocks such that the stack version of a block can be retained and released. So you can stick it inside, as a retained property of some of some other object, as long as you let go of it before you're done, this works. It's not that recommended, though, because lots of crashes and booms can happen if you're not very careful about that. For standard practice, you should do the copy. And if you're under, in this case, it's sort of like an instance variable, so release it before you reset it. So copy is the primitive to use. Copies of blocks that are already on the heap are cheap. So don't be afraid to use copy here. Another subtlety that came up is reflected in this by analogy. So as C programmers, we're very conscious of stack allocated memory. So if I had an array of pointers to things and I allocated inside that for loop a structure and remember the pointer, are we going to get 10 different versions of that? No. We're going to get a pointer to dangling memory, 10 copies of that pointer to dangling memory, and things are going to go boom, or if they don't go boom, you wish they would have gone boom, because something funny is going to happen. So the same thing is going to happen with blocks. If you try to capture blocks inside either an if statement, an if-then-else compound statement, or inside a for loop, it's going to sort of not work. It's going to go boom. And the answer here, of course, is to make a copy, to try to capture all the locality of each version of that iteration. You're going to need a copy of them to preserve them, and then if you're not using a garbage collection, you'll need to remember to do releases on them as well. I saw this once, thought it was worth telling you about. In this case, we're trying to build a smart kind of logging function. And only sometimes do we use this boilerplate method, or boilerplate object. But when this block that uses that gets copied, the runtime doesn't know that you're not going to use it sometimes. It's always going to try to copy the value of that boilerplate variable. In this case, it's uninitialized, and so you get a big memory smash, or something happens that's bad. So, this might be obvious after 20 minutes of thinking about it, but if you remember this and it happens to you, hopefully it'll take less than 20 minutes. Debugging, I just have a really easy story to say. It just works. These block expressions are, as I said, copied by the compiler into a function. It's very much like that sorting example. The compiler generates a custom structure. It allocates one right near where you use it. It fills it all in. But from the debugging viewpoint, you can set breakpoints in the middle of them. The local variables look like, all the variables you captured show up just the way you want them to, and it's really nice. And Instruments does a great job of monitoring blocks use within GCD. So, we've gotten full support of blocks for C and Objective-C in both GCC 4.2 and the new compiler Clang. Our support for C++ is not as complete. I'm sorry, I wish it were, but there's only so many hours in the day, and there is preliminary support available, but don't start a huge project expecting, anyway, be careful. We have published the specification externally as part of the Clang open source. As of 4 hours ago, we have published the runtime as well. We like the idea of people using blocks in places other than Apple, and we're trying to really put some meat behind that statement. So much so that, in fact, in addition to garbage collection, we presented blocks to the C Standards Committee. The C Standards Committee reaction was kind of interesting. They've been taking a lot of work that's been kind of falling out of the C++ standardization efforts, and there's a C++ kind of idea around closures, which they call lambdas, but lambdas can't really be copied. and stored and used as callbacks or as those timer things. They only work in the synchronous cases. Now, we think that blocks are far more versatile, and it turns out they're kind of, compatible and interoperable. So we don't see this as a collision. But from the C perspective, we can implement blocks in C, whereas they cannot be, the Lambda proposal cannot be brought back to C. So we'll see what happens with this. For more information, of course, contact Michael Jurowitz, who is actually not going to be here today for this talk. Under documentation, there's a COCO, programming topics area, and then there's a subtopic, the Objective-C language, and under there are 3 other docs that all describe stuff that Patrick talked about, garbage collection, the new runtime. We've got lots of APIs in our new runtime, and then we, of course, have a good document on blocks themselves.